Section 3.2 of linear algebra. Today we're looking at linear mappings, which are a special kind or type of mapping. 3.1 was all about mappings in general. Now we want to look at linear mappings. All right, so let's begin. Let V and V prime be two vector spaces over scalar field K. A linear mapping F from V into V prime is a mapping that satisfies two properties. First one, LM1, for any two vectors, U and V, we have F of U plus V equal F of U plus F of V. And number two, for any scalar C and K in V, we have F of CV equals C times F of V. So that's the definition of a linear mapping. Certainly, an old-fashioned straight line function in college algebra, f of x equals mx plus b, slope-intercept form of a line, as long as it passes through the origin. Now, it would have to pass through the origin to qualify as a linear mapping. So f of x equals mx, where b equals 0, where the y-intercept 0, would be a linear mapping. So lines that pass through the origin are linear mappings. Now let's look at the first example. Very important example. Example 1. This example identifies finite dimensional vector spaces as being equivalent, or what we call isomorphic to, Kn. All right, here we go. So suppose we have a finite dimensional vector space V having dimension n, okay? And let B, V1, V2 to Vn, be a basis for V. Define a mapping F going from V into Kn in the following way, such that for every vector V in V, F maps V to its coordinate vector, x in Kn, where the notation bracket V sub B equal x is the coordinate vector of V relative to the basis B. Remember, we defined coordinate vector earlier. Then F is a linear mapping. The proof is straightforward and you are responsible for it. So let V be an arbitrary vector in V that's represented by the unique scalars x1, xn in K, linear combination, x1 v1 to xn vn, and let W be another vector in V represented by its set of unique scalars y1 to yn. Okay, where f of V equals the coordinate vector x of V, and f of W equals the coordinate vector y of W, where x is x1 to xn and y is y1 to yn. Now look at the sum of V plus W. Well, if you do the arithmetic and then reassociate the scalars with their like terms, you get V plus W equals x1 plus y1 times v1 plus x2 plus y2 v2 plus dot 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 plus x sub n plus y sub n v sub n, so that f of v plus w is equal to x plus y, which in turn is what? F of v plus f of w. And similarly, if c is a scalar, where cv is just cx1 v1 all the way out to cxn vn, then f of cv equals c times x equals c times f of v. And so we have shown then that this mapping is indeed a linear mapping. Now, something else that you ought to prove for yourself is that this mapping F is bijective. It is injective and surjective. It's one-to-one and onto. And this defines what's known as an isomorphism, which means that the finite dimensional vector space V is equivalent or isomorphic to Kn. Now, this doesn't mean that V is equal to Kn, but it does mean that V and Kn operate in the same way, and that they are equivalent via a bijective linear mapping. Okay? Now next, we have another example with projection mappings. Projection mappings are linear maps. Say example 2, this is the generalized form of it. Let R and N be positive integers with R less than N. Then the projection mapping F that projects Kn onto Kr by f of x1, x2 to xn equals x1, x2 to xr is a linear mapping. That is, whenever you knock off xr plus 1 to xn, you have, again, a linear mapping. It's very simple to see that. Usually, you've seen such projections going from maybe R3 to R2 or R2 to R1 or R3 to R1. Okay. Now next, the generalization of example 3 is the following. Let A be an M by N matrix over the field K. Define a map L sub A going from Kn into Km by the following definition. L sub A of x equals Ax for all column vectors x and Kn. Then we contend that L sub A is a linear mapping. And the proof is simple. Let x and y be column vectors in Kn and let C be a scalar. Then number 1, L sub A, to show us a linear mapping, we have to show the two conditions. L sub A of x plus y is A times x plus y, but matrix multiplication is distributive across addition. So that's equal to AX plus AY, which in turn is L sub A of x plus L sub A of y. And number 2, L sub A of CX, which is A times CX, equals C times AX, equals C times L sub A of x. We know that scalars go float anywhere you need them. And so L sub A is the linear mapping associated with the matrix A. So anytime we have an M by N matrix, this is the linear mapping associated with that matrix. Okay. Now, just as a side note, we will note that the identity map and the zero map are both linear mappings. So, the identity map I sub s, I of x equals x, where S is the vector space V, and the zero mapping that maps every vector V in V to the zero vector of V prime, there's certainly linear mappings trivially, as you can show. I'll let you do that. There it is, example 4 and example 5. Okay? Now next, we're going to define the space, the vector space of linear mappings. So in higher mathematics, we're always generalizing ideas and making them more and more abstract. So example 6 is the space of linear mappings. Let V and V prime be two vector spaces over field K. The set script L, V to V prime, is defined as the set of linear mappings, say F, going from V into V prime, where F is a linear map. Now, this set of linear mappings is a vector space with the usual definitions of addition and scalar multiplication of functions. So if F and G, say, are linear mappings in L, then the usual definitions, with the usual definition of addition and multiplication by scalars. F plus G of U equals F of U plus G of U for all U and V. And when C is a scalar, CF of U is C times F of U. Now, you'll notice in the textbook that there's a long explanation that these definitions are indeed linear and form linear mappings. So I'll let you read the details of that in the textbook. It's very easy to follow. I just didn't feel like writing it all down. And then example 7 is an example of the vector space of differentiable real valued functions. So if we let V equal V prime be the set of functions going from the reals to the reals, where F has derivatives of all orders. And my notation for that is D infinity over the real numbers. So derivatives of all orders. Let capital D be the derivative, okay? Then D going from V to V is a linear mapping. For indeed, we know that the derivative of a sum of two functions is the sum of the derivative of the two functions, d of f plus g equals df plus dg, and number 2, the derivative of a scalar times a function equals the scalar c times the derivative of the function. That's just basic Calc 1, isn't it? That we know, that we've known for years. So we can now generalize the definition of a linear mapping from not just using two vectors and one scalar, but we can use n vectors and n scalars. Note, if f from v to v prime is a linear mapping, and if u1 through u sub n are vectors in V, and C1 through C sub n are scalars in field K, then we can generalize the definition of a linear mapping to n vectors by saying that f of C1 U1 plus dot 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 plus C sub n U sub n equals C1 f of U1 plus C2 f of U2 plus dot 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 plus C sub n f of U sub n. And this is easily shown, easily proven by using induction. And I would encourage you to do it for yourself. So prove this generalization for yourself using induction. It's very simple. Okay? And then finally, we're going to look next at a theorem 2.1. Theorem 2.1 on page 56. Now, Theorem 2.1 on page 56 tells us that linear mappings are completely defined by how they act on any given basis. That's what the theorem is talking about. Theorem 2.1, page 56. Let V and W be two vector spaces, and let B equal V1 through V sub n be a given basis for V. And then let W1 through Wn be any arbitrary vectors in W. Then there exists a unique linear mapping, we're going to call it T now, going from Vn to W, so that T of V1 equals W1, T of V2 equals W2, dot, 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 all the way out to T of V sub n equals W sub n. And if x1 through xn are scalars, then it must be the case that T evaluated at the linear combination x1 v1 plus dot 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 plus xn vn equals x1 w1 plus dot 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 plus x sub n w sub n. I have written an abbreviated proof in my handwritten notes, so let's look at it. Okay. Let V be an arbitrary vector in V, so we know that it can be written as a unique linear combination of the basis vectors v1 to vn with a unique set of scalars x1 through xn. Okay, so let T of V be the linear combination. This is a definition now. x1 w1 plus x2 w2 plus dot 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 plus x sub n w sub n. Then T is one such linear mapping. Now, the proof that T is a linear mapping is shown in your textbook on page 56. I just, again, didn't feel like writing it down by hand. It's simple to follow. So we've proven the existence of such a linear mapping, and then finally, we want to show that it's unique. And so we show it's unique by supposing that F, V to W, is another such linear mapping. Then F, evaluated at the same linear combination, suppose F is linear, okay? Then F of the linear combination x1 v1 to xn vn is equal to x1 f of v1 plus x2 f of v2 plus dot 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 plus x sub n f of vn, which, assuming it's another such creature, equals x1 w1 plus x2 w2 plus dot 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 plus x sub n w sub n. So we've shown that F is the same as T. So T is unique. So again, this theorem 2.1 here is telling us that linear mappings are completely defined by how they're defined on a basis of the vector space. So if you know how the definition of a mapping is defined on their basis vectors, then the linear mapping is completely and uniquely determined. So that's what theorem 2.1 tells us. So homework 5 is on page 57, exercises number 2 and 7. And I would also encourage you to look at number 1, number 3, number 5, and number 6 as well. But we're going to turn in numbers 2 and 7. So that concludes our video for Chapter 3, Section 2.